Hello everyone, thank you for coming to the talk. I am Shruti Tople and today I'll be talking about our work OblivP2P, a protocol for an oblivious peer-to-peer content sharing system. Traffic analysis is a well-known problem in the area of peer-to-peer systems. Content sharing systems like BitTorrent and others have reported heavily to users of millions of users per month, which is around 3.35% of overall world bandwidth. In these systems, peers usually communicate with each other to access resources for ease of availability and efficiency reasons. But with this benefit comes a drawback where these peer-to-peer systems are susceptible to long-term global traffic analysis through adversaries or organizations that have access to the network traffic or through devices and tools that allow global monitoring. We ask the question that with these capabilities, what can an adversary do by observing the network traffic between the peers in the network? The adversary can learn substantial private information about the users through several leakage channels like the plain text data, the length of the messages, and the time interval. Previous work has heavily focused on these side channels and proposed solutions like secure channel, padding of messages, and fixed interval messaging. If we assume that these defenses are already deployed and exist in the peer-to-peer systems, what we show in this work is that the adversary can still learn enough information by simply observing the access patterns between the peers in the network. By access pattern, what we mean is that which peer is accessing which resource and communicating with which receiver in the network. A global adversary who is observing this can easily link senders and receiver in the network and understand information about the resources exchanged between them. What is the problem with the current solutions that are used to hide this linkability property? Anonymous systems such as mixed network and Tor are good enough to hide online identity of users and guarantee anonymity properties. But these solutions fail to guarantee the property of unlinkability outlined earlier in presence of an adversary who has both long-term view of the traffic and global view of the entire network. This leads us to ask the question, is anonymizing sufficient to hide unlinkability? As a contribution in this work, we present OblivP2P, a protocol that guarantees unlinkability between the peers in the network while allowing obliviousness of the access patterns in P2P systems. We present a prototype implementation of our system and have made it available online on this link for users to download. Finally, we evaluate our system and find that OblivP2P has no centralized bottleneck on any single entity, and the performance of our system linearly scales with the number of peers in the network. Now let's step back and look at what is the actual problem and why are existing solutions insufficient in providing the unlinkability guarantees. Consider a peer-to-peer system that is using the mixed network as a solution to guarantee unlinkability. Here, the senders can submit their information to the mixed network where it is re-encrypted and permuted and distributed to the receivers. A global adversary who observes this communication cannot learn which sender is actually transferring which resource to which receiver. Thus, what we get is unlinkability for the single round. But let's see what happens when the same adversary can observe over arbitrary number of rounds for a long term and see what communication is happening in the network. This adversary can now do an intersection between the senders and the recipient sets of the people and understand what are the common participants in the network and create a link between the senders and the receivers, thus again getting the property of unlinkability through long-term capacity. This is a very well-known attack called as intersection hitting set or statistical disclosure attack for mixed networks with an adversary who has long-term observation capacities. In our work, what we propose is making the access patterns oblivious in peer-to-peer systems using the well-known cryptographic primitive of Oblivious RAM. ORAM is essentially proposed to hide access pattern between CPU and memory, where the data is shuffled periodically in the memory to hide the access patterns. ORAM is applied to various other areas like cloud storage and file system to hide access patterns. This makes us wonder, can we just take ORAM and directly apply it to peer-to-peer system to achieve similar guarantees of obliviousness? Before I get into answering this question, let me give you a quick background about ORAM. In our work, we use the tree-based ORAM, where the data blocks are arranged in a tree pattern, and there are two operations, read and write. For reading a particular block, what ORAM does, it fetches a path that contains a block, and that path is then stored on the local storage called stash. For writing blocks to this tree, it selects a random path in the tree, and the blocks are shuffled between the stash and this random path. With this background, now let's see how we can map the ORAM scheme to our peer-to-peer system. Let's consider a client-server model that is using ORAM. The client is trusted and stores the position map of the blocks and the stash. The server is untrusted and stores the data blocks in a tree pattern. Whenever the client wants to access a particular block, it will look up into its position map and fetch a random path that contains the block. Next, the client can decrypt the block and get the resource. A global adversary who is observing this communication sees that the client is just accessing a random path every time to access a resource. Thus, he learns nothing about actually which resource is accessed from which memory. Mapping this solution to our P2P system, we use a trusted tracker. A tracker is also present in BitTorrent-like system, which manages the communication between the peers in the network. This trusted tracker, similar to the client, holds the position map and the stash. Now, the peers in the network play the role of the storage devices and store the blocks in the tree pattern depending upon their storage capacities. They can either store one or more blocks of the network. Finally, whenever a peer who is a part of the network or outside, we call this peer an initiator, wants to request for a particular block, it will contact the tracker. The tracker, similar to the client, looks up into its position map and fetches the correct path that contains a block. Now, what the tracker can do, he can just send the ciphertext of the corresponding block to the initiator. But this is not secure because a global adversary who is observing this communication can see that the ciphertext that is sent to the initiator and the ciphertext that is fetched from the peer that holds the block is the same and learns eventually that the initiator requested the block from this peer. Hence, what the tracker does, it decrypts the block on its local server and then re-encrypts and sends it to the initiator. This solves our problem and guarantees obliviousness. That is, the adversary again, who is observing the communication, sees that the tracker is randomly accessing a path irrespective of what resource is accessed and does not learn actually which resource is being fetched. This solution we call as our OblivP2P 0 protocol. Even though OblivP2P 0 gives our security guarantees, it is not efficient. The tracker here mainly becomes a bottleneck because every time a request is made, the tracker has to fetch blocks of order of log(n) from the network. We do a quick evaluation of this scheme and see that OblivP2P 0, the tracker has to fetch almost 118 megabytes of block per request when the network size is of 2 million users. This is almost equal to the maximum bandwidth that the server can support in our experimental setup. What this makes us realize is we need a distributed oblivious peer-to-peer protocol. As a solution, we next present Oblivious peer-to-peer 1 protocol. The naive approach of converting the 0 protocol to 1 and removing the bottleneck is that whenever the initiator requests a block to the tracker, just make the tracker send the actual path, position and the key to the initiator instead of himself fetching the entire path from the network. Now the initiator can fetch the path that contains the block and then decrypt it on its local machine and get access to the resource. As we can see, with this simple tweak to OblivP2P 0, now we have made our protocol performant as the tracker does not actually transfer any of the real blocks, hence not becoming a bottleneck. But this scheme still suffers from a security problem. Let us see what is exactly that security problem. How ORAM works is while writing blocks to the tree, it writes the most recently accessed block to the top of the tree. And eventually, during the write operation, the blocks are pushed down, which makes the least frequently accessed blocks stay at the leaves. For example, let's take this particular path. Here we can easily know that the block 5 is less frequently accessed, whereas block 1 is the most recently accessed block. Thus, if an initiator requests for block 1 and it knows that the position in the path is at the top of the tree, it will know that this block has been recently accessed by some other peer, thus leaking private information about the blocks accessed by other peers. This is a well-known problem called as the block history problem, and it appears mostly when the resources are shared between many users. Hence, this security flaw also appears in our peer-to-peer system because multiple users access the same resource in P2P systems. For example, 2 people can access the same website or download the same movie, thus becoming the owner of that particular resource. To solve this challenge, we propose our new primitive, which we call as Oblivious selection. Oblivious selection guarantees that we can select a particular block without actually learning the block position, the cryptographic key, as well as not having any centralized bottleneck in the system. Let me present you the construction of our Oblivious selection primitive. As a first step, we use the cryptographic primitive of private information retrieval on top of the ORAM scheme that we are using for OblivP2P 0. Using PIR, what we do is we obliviously select a block from a path that is returned by the ORAM protocol. Note that we could directly use PIR to fetch obliviously a block from the entire network, but that is not efficient as it is linear to the number of blocks in the network. Using PIR over ORAM makes it efficient as now the operation is just logarithmic to the number of blocks. Now, whenever an initiator makes a request to the tracker, instead of actually fetching the path from the network or sending it to the initiator, he selects M peers in the network, and each of these M peers now downloads all the blocks that correspond to the path that holds the particular requested block. This path is now replicated at each of these M peers machine. The tracker further computes a PIR metadata corresponding to the requested block and sends it to each of these M peers. Now, every peer in this selected M peers has to compute an encrypted share using the PIR metadata and the downloaded encrypted blocks. Note that throughout this point, none of the peers actually know what is the block position of the requested block, and also observe that the trusted tracker is not actually transferring any of the real blocks. That is, there is no centralized bottleneck. All the operations are distributed among the peers in the network. More the peers in the network, more we can parallelize the computation, thus guaranteeing us the block position and no centralized bottleneck properties. But at the end of step 1, what we have achieved is every peer having an encrypted share. The next challenge lies in how we can decrypt the shares without actually revealing the cryptographic key. What we do for this is, as a second step, we use the primitive called seed homomorphic pseudo-random generator. Seed homomorphic pseudo-random generators allows us to decrypt shares without actually giving away the key to any of the peers in the network, including the initiator. After the first step, what every peer has is an encrypted share of the requested block. Now, the trusted tracker generates a valid key share for each of these M peers and distributes them. Finally, each of these peers uses their encrypted share and the key share that is submitted by the tracker and computes a decrypted share on their local machines. Note that even until this point, the peers that are selected have no information about what is the underlying plaintext of the requested block or the block position. What they only know is there is some decrypted share which looks like some random text to them storing at their local machine. As long as one of the M peers is honest, they cannot collude and combine each of their shares to get the decrypted block. The only way to do is to send the decrypted shares to the initiator, where the initiator will combine all the decrypted shares and get back the original decrypted block. Throughout this protocol, what we see is that including the initiator or the M peers or other peers in the network who are not participating in the protocol learn nothing about which resource is being accessed, what is the block position of the resource, or even the cryptographic key that is corresponding to the resource. It's only the tracker who has this information and is generating metadata about the requested resource and distributing the computation to the peers in the network. The second important point to note is that as in OblivP2P 0, OblivP2P 1 does not suffer from a centralized bottleneck, as every computation is distributed among the peers in the network. The trusted tracker is not transferring any of the blocks in the actual real blocks, but is only operating on position map and metadata corresponding to the requested block. Finally, using pseudomorphic PRG in step 2, we solve the problem of not revealing the cryptographic key and thus achieve our properties discussed before. As a security guarantee of our system, we show that in OblivP2P, any two equivalent accesses by two peers are indistinguishable for an honest but curious adversary, with the constraint that the number of dishonest peers or colluding peers who can talk to each other and share the information that they see while operating in the protocol is limited to order of n raised to epsilon, where epsilon is less than 1. We also gave a theorem to prove for this and provide a detailed proof in the paper. Lastly, we do an extensive evaluation of our system to understand its performance properties. We evaluate our system on Deterlab servers and simulate up to 16,000 peers on these 15 Deterlab servers. Each server in our network shares a bandwidth of 128 Mbps, and the block size that we use for the data transferred is 5 and 2 KB. We select this block size because it is similar to the chunks that are used in the BitTorrent system, so we wanted to keep consistency with the real BitTorrent network. The first result that we observe is that OblivP2P 1 has no centralized bottleneck. That is, the amount of data transferred through the tracker is independent of the block size, and it drops down to only 1 MB per request, as compared to the OblivP2P 0, the simple solution. The second important result that we see is that the throughput of our solution linearly scales with the number of peers in the network. That is, if you see from the network size 2 raised to 5 to 2 raised to 14, the throughput keeps on increasing and it becomes stable after that. What we see is that the throughput is 3.59 MB per second for 2 raised to 14 peers, and it stays constant after that. This observation is that if we scale it to larger networks, the throughput can improve, and the 3.59 MB per second is due to the limited infrastructure in which we did our test. For example, we simulated 16,000 peers on just 15 servers, where the computation and the bandwidth was shared between the peers in the network. Where the bottleneck was computational, that is, the computation resources were limited and the peers had to share, slowing down the performance. Whereas in real BitTorrent networks, if we apply this protocol, every peer will be having a separate machine and separate bandwidth link and computation resource. So we expect that the performance will be better if this protocol is actually simulated on BitTorrent network. Finally, as our conclusion, we propose hiding access patterns in peer-to-peer systems. We propose OblivP2P, which is the first work to repurpose ORAM in peer-to-peer systems. And lastly, OblivP2P is linearly scalable and is highly parallelizable with the number of peers in the network. Thank you, and once again, the implementation is available online.
We have time for a few questions.
Thanks for your talk. As you noted in the beginning, whenever you do a read from an ORAM, you have to mix the things in the stash and write it back.
Yeah.
I didn't see that in the later part of your
Yeah,
protocol,
so that's more detailed. We have shown that in the paper. But what we do is we are using the Oblivious select as a primitive to perform the shuffling as well. So for eviction, what we do is we select the path from the network and the blocks in the stash, and we call Oblivious select recursively in the number of times so that the permutation happens each time and the positions of the blocks is changed.
So where does so you select M peers to
Yes.
do the PIR.
Yes.
Where do they get the stash data?
So the stash is also stored at one, the stash is distributed between the peers in the network. So, yeah.
The tracker gives
Yes,
them the
exactly.
stash. Okay,
Yeah.
thanks.
So thanks, Shruti. Very interesting ideas. I'm curious to hear your thoughts about the overall scalability of the protocol. So I think currently your protocol achieves throughput on the order of a few megabits per second. So I'm wondering if you could share some potential optimizations that the research community could think about in the future to make these systems more practical.
Yeah, so it's because first of all, as I mentioned in the talk as well, the tests were done on a very limited infrastructure where we were just restricted to 15 servers and we were replicating as many peers possible to increase the network size. If we extend that to actual BitTorrent network, which is having individual resources and the computation and bandwidth is separate for each peer, we can utilize that computation and make the computation more parallel and increase the performance.
Hi. What would happen if two people wanted to access the same block at one time?
Yeah, so for that purpose, like it's not mentioned in this paper, but to guarantee parallel accesses, what we do is we replicate the blocks in the network and create several copies of the same block so that whenever one peer wants to access, that same block won't be submitted to the other peer and a different copy and a different position will be accessed for the next peer.
Thanks.
I have a quick question while Brad sets up. It sounds like you would need everybody, all those communication lines between the peers and the tracker and the initiator to be secure channels because you're assuming there's a global adversary. So how do they establish secure channels? Do you assume that everybody knows each other's public key?
That I think we can just use HTTPS or SSL communication to establish a
But you need to know the identity of everybody, right? You need to, like, I need to know that, okay, this is a certain peer that I selected and this is their identity and therefore...
Yeah, that can be established. So whenever a peer wants to join the network, he'll first establish that, okay, I want to be a part of the network and installing a BitTorrent client. At that time, the secure connection can be established before the communication actually begins.
Okay, thanks. Thank you. All right, let's thank Shruti again.